Hello class. Today I'm gonna teach you about the following concept. All of this, that's the whole title of today's concept. I know it's a lot. So let's read it very slowly and very carefully. I'm gonna teach you about the interpretation of the solution to a system of two linear equations in two variables as the intersection point of the lines that represent such these equations. I know this sounds like a lot. I understand, but if I want to be very formal and precise about what we are doing, I actually need to write this title because this is in fact what we are doing, and it cannot be summarized in any shorter way. So try to read this very carefully, very slowly, many times, 3, 4, 5 times, until you understand what this means, and try to read it at the end of the class because in retrospective, you're going to understand what this means. Okay, very well. So what have we done about systems of equations? What are the systems? What are these systems? What have we done about this? Let's make a brief summary. Okay, in here I'm giving you two equations. So we have two equations, right? They are to be understood as a system because they are related to one another. Okay, when you take two equations in such a way that it has the same variables, what that means is that you have a system of two equations. In this case, we have two equations. So we now understand the reason for adding this word system, the reason for adding two equations, because that's what we have. And remember, we have linear equations. We only talk about linear equations, systems of two linear equations. What does this word mean? What it means is that the exponents of the variables in my equations is 1, at most 1. Something like this, if I wrote something like this, for example, you see, this is also a system of two equations, but these equations are not linear because of this, because of this, because of this, and because of this. Okay, so we are restricting ourselves, we are restricting our study to systems like this. And the reason for this part in two variables, that's because each of my two equations has only two variables, x and y, because I can produce, for example, something like this: 3x minus y plus 2z equals 1. This is one equation, and maybe I can write another equation in this way: 5x plus 2y minus 5z equals 2. So in here also we have a system of two equations, but in three variables, x, y, and z. And this is not what we are looking at. Okay, we're gonna restrict ourselves in this semester to this type of systems only. So you need to understand why they are called system of two linear equations in two variables. Even though the name is very long, that's what they are. And so we have to call them by the proper name. Okay, so this is what we have. This is what we have been studying. And we know that we can solve this system by two methods, either the substitution method or the elimination method, also known as the addition and subtraction method. So we have two methods to solve this system. Each method works perfectly fine. It's up to you which one to use. It doesn't make any difference. And what I want you to do now, right now, is pause the video, take maybe a couple of minutes or 3, and I want you to solve this system of equations. So let's pause it right now and do it. Okay, so by now you should have been done with that task, and you should have found that the solution to this particular system is the following. the x solution is going to be minus 2 over 3. Try to keep the solutions as fractions, please. If you wrote minus 0.0666666666, that's also okay, but this is the best way to do it with fractions. And your y solution will be minus 1/3. Okay, in the context of systems of two linear equations in two variables, the solution to a specific system is usually written in this way. This solution, which is perfectly valid, perfectly okay, is usually written in this way as a point. You remember points? X comma y. You remember that? Okay, so you write two parentheses, the comma, and then you put your x solution first, and then your solution for y. So this is my solution. Okay, either you can write either this is perfectly good, this is also good. So they are interchangeable. Now we need to understand why this method, why writing it as a point. What does a point, a geometric point, have to do with this stuff? Okay, that's what we need to understand. Okay, so that's the second part of this explanation. That's this part. Yeah, I'm gonna do it in blue. The interpretation of the solution to a system of two linear equations in two variables as the intersection point of the lines that represent these equations. So what do I mean by a line representing a linear equation in two variables? What does that mean? It means the following. If you're noticing here, I have drawn a Cartesian plane. You have already used this concept in mathematics, in junior high maybe. And let me tell you that we can do something very, very cool with an equation in two variables, a linear equation in two variables, and this system. We can represent visually an equation like this, or an equation like this, or any other type of linear equation in two variables. We can represent it visually or graphically in a Cartesian system like this. What do we do? What we do is the following. I'm going to first begin with my first equation. I'm going to write it down in here again. Sorry. Like that. And what you do is the following. If you notice, guys, when you just have an equation like this, like isolated, don't even think about the other equation for a moment. Okay, just think about this equation. Just think about this. Look at it. Look at it. If you notice, this equation, we can say that has many solutions, many possible solutions. What do I mean by this? Well, something like this, has only one solution, right? For the x variable. What's going to be the solution for x? It's very simple. X is going to be equal to 1, right? Because 2 times 1 is 2, plus 1, 3. Perfect. So this checks, and this is my solution, and it is unique, and it's only 1. You see? But this is an equation with just one variable. Now look at this. You have an equation in two variables. And we can look at this and say that it has many solutions in the following sense. For example, if you chose a particular value for x, for example, the value 1, choose x equals 1. Then what that means is that for this particular value of x, for x equals 1, we're going to have a corresponding value of y. How do we find it? Well, it's very simple. You just choose this value for x, you put it there, right there, and then you solve for y. What that means is this. We have 2 times x, but I chose x to be 1, so we write this, and then we continue minus y equals minus 1. And then, as you can see, I have produced an equation with just one variable, which is y, and therefore we can solve it. So let's solve it. We're going to have minus y equals minus 1 minus 2, or in other words, y equals 3. So this is my solution for this particular value of x. So I'm going to write this. For x, I'm going to write this, and I'm going to say the following. For x equals 1, the corresponding value for y is 3. And I can represent that as a point because I want to. You know, in mathematics, you have freedom of expressing many things in many ways, or you have some creative capacity. And I'm gonna say that this represents a point in this Cartesian plane, the point 1 comma 3. You see, like that. And you can do this process many times with any numbers you want. For example, if now you give the value of 2 to the x, for example, well, I'm gonna make a division here for clarity. Let's give it the value of 2 to the x, and let's do the same process. I'm gonna plug the value of 2 right there, so it's gonna be 2 times 2 minus y equals minus 1, and then you solve this equation. I encourage you to solve it on your own, and you will get 5. Make sure of this, please. Pause the video and make sure. So you're gonna get this, and again, I'm gonna represent this couple, which is a solution. This is a solution to my equation. I'm going to represent it as a point, 2 comma 5. You see? And I can do the same with any number, with any value of x that I want. Negative values, fractional values, it doesn't make any difference. I'm going to choose one negative and fractional value, like so. For x equals minus 1/2, what y will you get? Well, do the same process. Do the same process. I'm gonna substitute this value in my x. So I'm gonna write 2 times minus 1/2 minus y equals minus 1. Stop the video, solve this equation, and you will get that y will be 0. 0. Let me check to be sure, to be completely sure. So minus 1. Yes, that's right. This is gonna be 0. Okay, so we have another solution. We say that these two numbers together, this couple, x equals minus 1/2 and y equals 0, is a solution to my equation, because when I replace this number right there, when I put it right there, and when I replace this number, which is y, and I put it right there, my equation will be true. That's why it's called a solution, guys. You see, because you have to replace, you have to go back to the equation, and you gotta check that it's satisfied. So this is in fact a solution. Let me erase the recent blue lines. Okay, and so we have another point as a solution, the point minus 1/2 comma 0. So we have 1, 2, 3 possible solutions to this equation. How many are there? An infinite number. You can do this, you can spend hours and hours. X equals 1000, and then you get the value of y, and x equals whatever, and you get the value of y, and you will get many possible solutions represented as points, like so, or in this way also. And what you can do in order to represent this whole set, all of this set of possible solutions, which is infinite, I repeat, you have infinitely many possible solutions, okay, infinitely many. A way to represent this is in the following graphical way. What you do is you pick one of them and you graph it. 1 comma 3, where is that? It's 1 comma 3. Well, I think if I do further subdivisions, this will look better. Let me quickly, 1, 2, 3, 4, 5. There you go. There you go. There you go. So 1 comma 3, I'm gonna put that point in yellow. So we have in the x-axis we move one place to the right because that's the direction of the positive numbers, to the right, and this number is positive. So we go 1 and then comma 3, which is upwards because it's in the y-axis, and upwards because it's positive. So 1 comma 3, it's right there. This point is right there. Remember it. Now 2 comma 5, I do the same. 2, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and then 2. It's this point. You know, when you do this stuff with ruler, and when you do it very carefully, everything looks very nice, and there is no chance of confusion. And then this one, minus 1/2 comma 0. So minus 1/2 is just right there, and then 0, it's, well, it's right there. You see? And if I kept searching for other solutions, I'm gonna find a huge amount of points in here in this yellow whatever, this yellow enclosure. So basically, when you do that, guys, you're gonna come up, or you're gonna be able to graph a lot of points. Look, we have 1, 2, 3, but there are many points in the middle, in between them. There are many more points, all of them representing all of these guys representing a possible solution from this set. You see, and when we do a lot of them, and we trace a smooth line, okay, along those points, what's gonna be created? I'm doing my best. Okay, what's gonna be created? It's a line. That's it, guys. You see, that's why a line, a line in the Cartesian plane represents the possible solutions to this, in this case, to this particular equation. Or we can also say that that this line represents the equation itself. You know, it's two possible ways to see it. You can either say that it represents the solutions, all the possibility of the solutions for this particular equation, or sometimes we say that this line in fact represents this equation. You see, and that's what you do. You give values to x, you get the corresponding values of y. You represent these solutions as points. You go to the Cartesian plane, you graph those points, maybe some 3 or 4 or 5. You know, you don't have to do a lot. It's not necessary. And then you trace a straight line over them. And this line represents your equation number 1. You see how easy it is? That's it, guys. That's what we mean by a line representing an equation, you see, in two variables, a linear equation in two variables, a linear equation in two variables. And that's how it works. Now, let me erase all of this very quickly. Now that you understand what you have to do, there you go. Okay, now you're gonna do the same for this other equation. I'm gonna go with blue for this other equation. Okay, for equation number 2, you are supposed to do the same process I did in here in order to find the line representing the equation 1. Do the same for blue. Do the same for the equation number 2. And you will find that, for example, some possible points. This one is much easier, right? For example, for x equals 1, we have that y will be minus 2. So you can confirm that this in a moment. It's very simple to realize what I'm saying. So the point is 1 comma minus 2. For x equals 2, the corresponding value of y is, we have, it's going to be minus 3. 2 comma minus 3. For x equals 0, y will be minus 1. For x equals minus 1, we get that y equals 2. Let me check if I'm doing everything right. Yes, 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 that's right. So when you do this, guys, you're gonna come up with these points, these solution points. You see, and you do the same. You take these points, you go to your Cartesian plane, and you graph them. 1 comma minus 2. That's gonna be this 1 comma minus 2. It's right here. Okay, 2 comma minus 3, 2 comma minus 3, 0 comma minus 1, 0 comma minus 1. It's not gonna look very good. It's to the left of this yellow line. Minus 1 comma 2, minus 1 comma 2. uh, no, I think I made a 0 comma minus 1. Yeah, I made a mistake. I made a mistake in the previous one. I'm so sorry, guys. This point is not there. It's 0 comma minus 1. So it's going to be 0 comma minus 1. It's this point. That point. Sorry about that. And I think I also made a mistake in here. Did I? Minus 1 comma 2. Okay, okay, it's fine. I'm checking because I think I made a mistake, but I'm just checking. 1 comma minus 2, 2 comma minus 3. Okay, these points are fine. 0 comma minus 1. Okay, and then minus 1 comma 2. I think this one is wrong. I don't know why. Okay, let me check this one in a moment, guys. I'm getting confused, but these points are correct. These points are correct. And so what we get when you actually draw the line over those points, it's very difficult to do. There you go, more or less. Okay, so basically what you can find, guys, is that they cross at about this point. Okay, right there. Look at this point. Look at that point. And that point has approximately, well, not approximately, this point, if you can see, it's actually this point. Can you remember what this point was? This was the solution to this system of equations. It was a point minus 2/3, comma, minus 1/3, which is supposed to be this point. Of course, it doesn't look that good in here. It's hard to do this thing with this uh, process, with this tool, but it's this point. It's minus 2/3, comma, minus 1/3. It's this point right there. It's the point at which the line 1, which is represented, which is representing this equation, and the line blue, which is representing this equation, at the point that they cross, what that means is your solution. It's your solution to the system of equations, which is supposed to be minus 2/3, comma, minus 1/3. That point, this point is right there, guys. Right there. Okay? So that's what it means, guys. That's what we mean by a line representing an equation and interpreting the solution to a system of two linear equations in two variables as the intersecting point of the lines that represent each of your equations. Maybe I should have chosen a more um, mm, like a more understandable example, like the intersection point being in another place, not so close to this origin, because it's not looking very very well. But well, I already did it. Okay, I'm gonna repeat this process very quickly in tomorrow's class so that you understand it perfectly well, because this was not the best example. Maybe it was not the best. So I think you have an idea already of how this works, and by understanding this that I just did, you can now solve these problems, right, from exercise 3.4 only the odd exercises. The first one is very simple. It says find the intersection of the lines below. Well, all you have to do is just basically, I'm gonna erase this. I mean, all you have to do is spot the point at which they intersect, right? In this exercise, you have the point 2 comma 5. Well, it's not looking well. This is the point 2 comma 5, right? It's 2 and then 5 units up. What about this point? What is the intersection point? It's the point 3 comma 0. So I believe you can do this on your own very, very easily. Okay, so the exercise one shouldn't give you any problems, any difficulty. And the exercise 3 is very similar to what I did a moment ago. It says find the intersection of the following pairs of lines. So each of these equations is being represented by a line, and basically all they want you to do is get the solution of this system of equations and represent it graphically, just like I did in this lesson. Also, you can solve, don't do this one yet, don't do 5 yet, and you can also do 7 and 9. 7 and 9 are very similar to the application problems that we have solved. Basically, you're going to have a system of two equations with two variables, and you gotta get the solution. Okay, just like the problem of the tickets in the fair, and the problem about what it was it bananas and apples that I told you about, and the ones that you worked at in the previous lesson. So that's it, guys. That's how it works. If you have questions, if you didn't understand fully, wait until tomorrow, until Friday, tomorrow, and I promise that you will understand it perfectly well. I'm gonna prepare a much better example. Okay, guys. So that's about it. See you tomorrow in the asynchronous class, and have a great day. And good luck in the exam.